In section 2.6, we're going to talk about systems of linear equations as well as some applications of those. A system of linear equations is simply a set of, in our case, we'll look at two linear equations. From a graphical perspective, if we graph two linear equations at the same time on the same axes, not always, but much of the time, those two lines are going to intersect. And this point of intersection right here is what we call the solution to the system of equations. What's actually special about that point? Well, if that point is, let's just call it A, B for now, then when x is A and y is B, it makes the first equation true because the lines, or that point is on this line, and it also makes the second equation true because the point is on that line. So what's special about this point is it makes both linear equations true. All right. In many cases, we are not given our lines as actual functions. Sometimes we're not solved for y or given in function notation, but they're still lines. And in most of this section, we'll actually look at problems where we're not necessarily given the function notation to start with. Sometimes we will, but not always. I want to look at a few different ways of finding a solution to a system, or in other words, an intersection point, using algebra, and then we'll use a graphical method, Desmos, to check. There are two methods that you've probably seen before: substitution and elimination. I'm going to start with our substitution method. In the substitution method, the basic strategy is we're going to solve one of our equations for y and then use the result to substitute for y in the other equation. Little note here, you don't actually have to solve for y. You could solve for x, or if your variables weren't x and y, if they were other letters, you could really solve for any letters. So you can really solve for any variable. Doesn't have to be y. It was just easier to type it up that way. All right, let's look at our first example. I'd like to solve this system of equations, and then we'll verify by graphing. So I really am looking for a point that makes both of those equations of lines true. Well, I can see that in this first equation, I've almost got y by itself. It would be pretty easy to solve that top equation for y, so that's what I'm going to do. If I subtract the 3x, y will equal negative 3x plus 10. And then I'm going to say, let's take that and let's replace the y in the second equation with what y equals, negative 3x plus 10. So my second equation now becomes 5x, subtract 3, multiplied by, instead of writing y, I'm going to put in what y equals, negative 3x plus 10. And that is supposed to equal negative 2. All right, I've got a little algebra problem to solve here. I've got my 5x, and then I'm going to distribute my negative 3. So that'll become a positive 9x and a negative 30 equals negative 2. So I have 14x minus 30 equals negative 2. I'll add the 30 to both sides. 14x equals 28. And then get rid of that multiplier. I got to divide by the 14. Always on both sides, of course. And it looks like x is equal to 2. All right. keep in mind, the solution to a system is an intersection point, so I need both an x and a y value. Right now I have an x value, but I also have an equation for y, so I'm going to go ahead and take that equation and I'm going to plug in this 2 that I just found for x. So that would be -6 plus 10, and y is 4. Now when you write the solution to a system, you can certainly just say x equals 2, y equals 4, but because that solution really represents an intersection point, we typically give the solution as an ordered pair, a point. So in this case, since x is 2 and y is 4, I'd probably write my answer as 2, 4. All right, we're going to check out our 2 lines, right? These are just 2 linear equations, x and y are to the first power. We're going to check those out in Desmos. We're going to graph them, and we're going to see if 2, 4 really is the intersection point. Fortunately, for me, for all of us, we can put equations into Desmos without solving them for x or y. We can type them in just the way they were given to us. 3x plus y equals 10. First line. And the second line was 5x minus 3y equals -2. Second line. And visually, you can probably already see the intersection point at 2, 4, but I can also click on it. And I can definitely see that, yes, those 2 lines intersected at 2, 4. The point 2, 4 is the only point that is actually on both lines. No other point is on both of them. All right, we're going to try an application where we get a couple of lines and we'll solve a system by substitution in our application here. If you've taken an economics class, you probably have heard the law of supply and demand. But basically, just sort of in a common sense way, it says that as the price of an item increases, the demand will decrease, but the supply will increase, right? So if price goes up, fewer people will buy it, right? It gets too expensive, you stop buying something. But if you're the manufacturer, you want to make more of them because, hey, you're getting more money for it now, right? So as price goes up, demand goes down, but supply goes up. And we could say the exact same thing in reverse if price went down. All right, we're seeing that law of supply and demand down here in this data table. It shows the sales, or in other words, the demand, for a particular brand of jeans for various price levels, as well as the available supply for the same prices. So if we are pricing our jeans between $20 and $30, pretty cheap jeans, I guess, you can see that the number sold per day is 60 when they're relatively inexpensive at $20 a pair, but as the price goes up, fewer people are buying them. Now, from the point of view of the manufacturer, when they were only making $20 a pair, they were willing to produce 48 pairs a day. But as the price went up, they said, hey, I'm going to make more of these things because they're making me more money. So supply went up. All right, we are supposed to verify that a linear model is a good fit for the demand data and find the line of best fit for that, written in the form n equals d of p. So price p and demand m. We will do that right away, and we want to round all of our values, it says, to 1 decimal place. So let me put my data in. There we go, and I'm going to use my zoom fit. All right, did I get all my numbers in there correctly? I think I did. 60, 57, 56, 52, 49, 44. Yep, I did. All right, so this is a good example of something where it's not a perfect line. You can definitely see that, right? But the problem said do a line of best fit, and we'll see that we should be able to get at least somewhat close to all of those points. So let's do that. y1 tilde mx1 plus b. All right, not too bad, right? The first few points are really close. These get a little bit further away, but notice that our r squared is still 0.94, which is really quite good. When it gets to be below 0.9, I start to think, the fit's not as good, but anything above 0.9 is really a pretty decent fit. So I'm okay with that as my line for the demand data. For my slope, I'm going to use negative 1.4, and for my y-intercept, I'm going to use 88.2. So again, just as a quick reminder, we did y1 tilde mx1 plus b. That gave us an m of negative 1.4 if I round to 1 decimal place, and a b of 88.2. All right, I want to write this in the form n equals d of p. So n, the number of sold, is function name this time is d for demand, which is a function of price p. And that will be negative 1.4 times the input, p, plus 88.2. It's just a little different than I've usually been writing these, right? I often wasn't writing the n equals part, but we can, right? I just this time chose to give my function a different name. All right, we're going to do the same thing for the supply data. Let's see how we do with that one. I want to show you something here. Up in your table, if you go ahead and create a third column just by clicking on it, we can actually include the supply data in the same table since the price points are the same. I can't use y1 again, so I'm going to label this one y2. And then I'm going to put in my supply numbers. All right, looking at the red points, the supply data actually looks even a little bit more linear than the demand data did. So I definitely think I can do a linear regression and come up with a pretty good fit on this one. Now, normally we use y1 tilde, but notice that my supply data here was in the y2 column. So this time I'm going to have to go y2 tilde mx1 plus b. Notice it's still x1 because I'm still going back to these input values. All right, notice it is a much better fit. This time I've got 0.998 as my r squared, so very close to 1. We can see that visually all the points are really close to the line. And if I round to 1 decimal place, I have 1.7 for my slope and 14.9 for my y-intercept. So this time, just as a reminder to you, if you look at this later, we used y2. I put this in the y1 column, and I put this in the y2 column. This was in the x1 column in Desmos, right? So I had to do y2 tilde mx1 plus b. And that gave me an m of about 1.7 and a b of about 14.9. All right, this time we want to write this in the form n equals s of p. So that would be 1.7 times the input variable, p, plus 14.9. We'll talk just a little bit again about naming conventions. I used N for both of these because both of these refer to the number of pairs of genes, right? So it kind of made sense to use the same letter for both of them. But to emphasize the fact that I had different functions, I named my functions differently. D of P for the demand equation and S of P for the supply equation. All right, question C. At what price point will supply and demand be the same? And it asks us first to solve by hand, and then we'll verify back with our graph. All right, in order to do this, I'm going to go ahead and I'm going to leave off the function notation piece, and I'm just going to write these as the N equals. The N's represent the same thing, the number of pairs of genes, and I already have actually both equations solved for N, so all I really need to do is substitute. I can take what N equals here and substitute it for the N here. And that should tell me where these lines intersect and therefore have the same price point. So substituting for N, negative 1.4p plus 88.2 equals this side, 1.7p plus 14.9. All right, I'm going to add the 1.4p. So I have 88.2 equals 3.1p plus 14.9. I will subtract the 14.9. Desmos to help me with a little bit of arithmetic here. That is 73.3. And then I'll have to divide by the 3.1. So let me do that. And I get about 20, it says not round to the nearest cent, this is a price, so to the nearest cent that would be 23.65. And there it is written out with the algebra. So it said at what price point will demand and supply be the same? At a price of $23.65, it all works out perfectly, right? The suppliers create or manufacture exactly the number of pairs of genes that the consumer demands. And we have this nice even outcome. All right, let's verify that with our graph. If I go back over here to Desmos, you can see that my demand equation here and my supply equation intersect right about there. And there is some round-off error here. That gave me 23.92. That's actually a little bit more accurate than what I got by hand. And the reason, of course, is, remember how we rounded everything to one decimal place? They kept all of these decimal places that they gave us. So that's actually just a little bit more accurate, but it's in the same ballpark, so I'm convinced I probably did this problem correctly. So I'm going to write down the intersection point that I got from Desmos. I want to talk just a little bit more about it. It is 23.92, comma, 54.75. All right, first of all, the input, the p-value, is pretty close to what we got by hand. The only reason it's just a little bit different is because of round off. Right, we rounded all of our values to one decimal place here, so that's why. But what is this number? Right, we didn't come up with that one. We could have if we wanted to, but we didn't. The output is the N value. So what this is saying is that if we price the genes at that magic number, $23.92, then both the supply and the demand will be 54.75. Now, as usual in a application problem like this, you have to take into account that realistically we never make part of a pair of jeans. So I might end up saying, at a price of about $24, both demand and supply are about 55 pairs of jeans, right? And so rounding in a final answer like that can kind of make it make a little bit more sense in terms of a specific situation. All right, so that's our substitution method. One textbook type problem, one application. We're going to do the same thing for the second method, the elimination method. We'll do one textbook problem, and then we'll do one application. In the elimination method, what we're going to do is we're going to multiply one or sometimes both equations by numbers that will cause one variable to be eliminated, to add up to 0 when the equations are added together. Keep in mind when you're multiplying your equations, be sure you always multiply both sides of the equation by the same number, right? Basic law of algebra. All right, so here we go. Here's my system of equations. And I could do this by substitution, but notice that if I try to solve for either x or y, I'm going to end up creating fractions. And lots of times we don't love working with fractions. So instead, we're going to go ahead and try this elimination method. Okay? You want to concentrate on either the x's or the y's. Your choice. I like to go with the one that has the smaller numbers. So I'm going to concentrate this time on the x's. I would like to have it so that when I add those, they're eliminated. In other words, I just end up with 0 x's. Now, it wouldn't be real hard to make that a -6 and that a +6. And that way they do add up to 0. In order to do that, I would have to multiply this top equation by 3. And I'd have to multiply this bottom equation by 2. When I do that, the top one becomes -6x plus 9y equals 27. Again, notice I multiplied through everything, both sides. And when I multiply by 2 down here, I'm going to get a positive 6x plus 14y equals -4. When I now add these equations, by design, the x's are eliminated. I have 0 x's. When I add them, I get 23y's equals 27 minus 4 is 23. So when I divide by 23, y must be 1. Now again, remember, solution to a system of equations should be an intersection point. So far I only have a y value. So I'm going to go back, and you can pick either equation. It really doesn't matter. I'm just going to use this one. And I'm going to plug in my y equals 1. Let's see, if I subtract the 7, 3x equals -9, and divide by the 3, x equals -3. So I now know both the x and the y value. That makes both of those equations true at the same time. I like to write that as an ordered pair, -3, 1. All right, let's check and just make sure that we did everything correctly, and that really is where those two lines intersect. Again, I can type these in just the way they look. I don't have to solve them for X or Y. One really nice thing about Desmos. Here's our intersection point, -3, 1, just as we predicted. It's the one point that's on both lines. All right, example 4 is, it's not a data example, but it is a descriptive example that's going to allow us to come up with a system of equations that will lend itself well to an elimination method. All right, a product is packaged two ways. Small quantities are packaged in cardboard boxes. Large quantities are packaged in wooden crates. A shipment contains 17 boxes and 8 crates and weighs 285 pounds. Another shipment has 9 boxes and 15 crates and weighs 420 pounds. Find the weight of a box and also find the weight of a crate. Well, we want to start by defining some variables, right? Two things we want to know: weight of the box, weight of the crate. So let's just let B equal weight of a box, and we'll let C be the weight of a crate. All right, take a look at what this sentence says. 17 boxes. If I have 17 boxes, the total weight of them would be 17 multiplied by B, the weight of one box. Plus, I also have 8 crates in this shipment, and each crate weighs C pounds, so I'm going to have to add 8C. And that equals the total weight of 285. Go ahead and try and set up a similar equation for this next sentence. Go up with 9B plus 15C equals 420. All right, so I've got a system of equations I want to solve. The numbers are a little bit more, a little bit less fun to work with. They're not quite as small, so I'll have to work a little bit harder on this, but we can do this. All right, I want to eliminate one of my variables. It doesn't really matter. The C's slightly smaller numbers, so I'm going to go with the C's. As I look at this, if I multiplied this one by 15 and that one by 8, I'll get the same number, right? But I actually will get the exact same number. And I wanted one of them to be negative so that I can eliminate the variable. So let's actually multiply by -8 in the second one. All right. My calculator here to help me out. When I multiply by 15, let's see, 17 times 15 is 255B, plus 8 times 15, 120C, equals 285 times 15, 4275. Next equation, I'm multiplying by -8. So -8 times 9 is going to give me -72B. 15 times -8 is -120C. And 420 times -8 is -3360. All right, I'm going to add these equations. So first, 255 minus 72 gives me 183b. When I add the c's, I get 0. Again, that's what we worked so hard to do. We designed it that way. And then I've got 4275 subtract 3360 is 915. I need to divide by the 183. Sorry, hit a wrong key. Let me try that one more time. And I get 5. All right, so we now know that the box weighs 5 pounds, right? B was the weight of the box. We still need the weight of the crate. And again, you can go back to either equation. It doesn't really matter. I'll just use this bottom one. Now that I know that B is 5, I'll be able to solve for C. So 45 plus 15C equals 420. I need to subtract the 45. 15C equals, what would that be, 375? And then dividing by the 15. 375 divided by 15 is 25. So we're going to conclude that the boxes weigh 5 pounds and the crates weigh 25 pounds. Now in a case like this, a word problem like this, I'd probably not bother writing my answer as an ordered pair because the variables have meanings. And so for my reader, I'd want to label them this way. But we know that 525 should be the intersection point of my two lines. So let's check. You know what? I wasn't sure about that, so I thought I'd try it. Sometimes if you don't know, you got to try stuff out, right? I tried using the B's and C's, and because it's not function notation, Desmos didn't recognize it. I think I'm going to have to go with X's and Y's. So let's do that. I'll just replace B with X, and I'll replace C with Y. And that way, notice it no longer gives me a little warning over here. I can't see it yet. That's my window. But at least it's not giving me a warning. So have to use X's and Y's, but that's okay. We'll reinterpret when we go back to our paper. Now I can't see anything yet, so I'm going to do a couple things. I am going to go ahead and change my y-axis till I start seeing that, and my x-axis as well. There we go. All right, let's put in our second equation, which was technically 9b, but I'm going to call that 9x. Plus 15y equals 420. And there's our intersection point at 525, which was exactly the values of B and C that we calculated by hand. All right. My next example actually kind of goes back to a previous problem that we did. Remember back in the early part of this chapter, we had that problem about the plumber and the electrician. Just a reminder, the electrician charged $80 an hour plus a $25 service charge. The plumber was $65 an hour plus a $40 service charge. And the question was to find the visit length that would result in identical charges for both professionals. So let's just real quick reconstruct our equations. The electrician I'll say that's E of H, where H is the number of hours. And let's see, that was $80 per hour, so 80 times the number of hours, plus no matter what, the $25 service charge. And for the plumber, we'll go with P of H for the plumber. That was $65 an hour, so 65 times the number of hours, plus the $40 service charge. Now, these we wrote as different functions, but they're both the amount of money. They're both the charge. So if I wanted to, I could set them both equal to C, where I'm defining C as the charge for the work done. And I could now say, oh, that means that if I use a substitution method, right? Substitution is going to be easier this time. I could just go ahead and I could take what C equals here and substitute it for the C in the second equation. So I'm going to go with the substitution method here. 80H plus 25 replaces the C, and that's going to equal 65H plus 40. And hopefully that kind of makes logical sense, right? You're just setting the charge for each professional equal to one another. All right, I want to solve this for H, so I'm going to subtract 65H first. I have 15H plus 25 equals 40. If I subtract the 25, I have 15H equals 15, so it looks like H is going to equal 1. If they each work 1 hour, they're both going to walk away with the same amount of money. I wanted to show you one more thing here. Let me go back to the beginning. I'm going to rewrite my equations without the function notation for a moment. This time I used a substitution method, right? I just took this and substituted in for the C in the other equation. Could you have solved this with an elimination method? You really could have, right? It wouldn't be very difficult to eliminate the C. All I'd have to do is multiply one of the equations by -1. So let's do this. I'm going to take the top equation and multiply it by -1. And now when I add them together, I get 0 for the C's equals -15H plus 15. I can add the 15H to both sides, and we get our H equals 1 again. So absolutely, there are many problems that are just as easy to solve with elimination as substitution, and you can pick whichever way seems most convenient to you. Either way, though, the question was, what's the visit length? 1 hour will result in the same charge for both the electrician and the plumber. All right, to wrap up this section, I want to consider the question, will every system of linear equations have exactly one solution? Well, first of all, hopefully it kind of makes sense. If you've got straight lines, right, two straight lines can't intersect in more than one place, right? They'd have to bend if they were going to hit each other more than once. So two lines are only ever going to have at most one point of intersection. They can't have 2 or 3 because they can't bend around. That said, there are a couple of special cases, and they're actually illustrated by these two examples. We're being asked this time to graph the lines. We're going to graph them on Desmos first, and then see what happens when we try to solve them by hand. So let me take this first example, and I'm just going to go ahead and type both these lines into Desmos and see what happens. There's our first line. There's our second line. My window isn't great. I probably could use slightly smaller numbers, but it's enough to see what I want to illustrate, which is the fact that these two lines are parallel, aren't they? They don't intersect at all. Since the two lines don't have any points in common, we say that this system of equations has no solution. All right, how would you know that if you were trying to solve a system of equations using algebra? Let's take a look. I'm going to go ahead and use an elimination method on this one. And I'm actually just going to concentrate right now on the y's. Can you see if I just multiply this by 2, I'll have a positive 2y and a negative 2y, and I'll be able to eliminate the y's. So that's what I'm going to do. I'm not going to change the first one at all, but the second one I'm going to multiply by 2. When I add my equations together, not only do the y's eliminate, I have 0 y's, but even though I didn't try to set it up that way, the x's actually eliminate as well. So I have no x's and I have no y's. In other words, I have 0 on the left-hand side of the equation. On the right-hand side, 6 plus 2 is 8. This is clearly a false statement. And this is your signal that you actually have no solution to a system. And in fact, the lines must have been parallel. There was no point where the two lines intersected or agreed. So if you're working algebraically and you get a false statement, you can immediately conclude no solution, parallel lines. All right. Let's see what happens in the second example. Again, I'm going to start with Desmos. I'm just going to type them both in and see what we get. So there's my first line. And the second one, oops, good thing I'm almost done. Did you see what happened there? The blue line was the first one, and the red line graphed right on top of it. These are actually the same line. So technically there are infinitely many points of intersection because they intersect everywhere. So same line, there's actually infinitely many solutions. If I were to show this algebraically, what I could do is I could take my first equation, which is already solved for y, and I can take that 3/2 x plus 3 and substitute it for the y in the second equation. So I have 3x. I'm going to distribute the negative 2. So here the 2's will cancel and I'll just get minus 3x. And then negative 2 times 3 is negative 6. 3x minus 3x is 0. So I have negative 6 equals negative 6. Well, that's a true statement. And anytime you get an equation that there's no x's left in it, but it's just true all the time, that's your signal that there are infinitely many solutions, and we really just have two different versions of the same line. All right, that brings us to the end of section 2.6.